Hi everyone, I'm Vina Ermagan, and today with Lori, Jakab, and Alberto, Rodriguez-Natal, we're going to give an overview of the ODL Lisp service and its use cases for SDN and NFV. So we started the Lisp service together with the context stream, some of the members of the context stream team basically, from the first release of OpenDaylight. And since then, over the past couple of releases, we have made many improvements to the service, both in terms of additional features and stability of those features. So today, I'll kind of give an overview of this service, and then where we started from and where we're going with it. And finally, we have a demo that captures some of the use cases, core use cases that we're targeting this for. And we show that live here with using only open source software. So this is our quick agenda. For those who are not familiar with Lisp, I'll give a very quick overview of Lisp, and that helps everybody better understand where it all started, basically. And after that, we'll move on to the core of what the ODL service is. And for those who are familiar with Lisp, there's more to it in the ODL service, so just bear with us for that very quick overview. And after that, we'll give some of the core use cases. We'll go over some of the core use cases that we're targeting the service for. And then we'll go into how the service plays within the OpenDaylight and an integration with the other services there. And then we talk about availability of various pieces of software that support Lisp in the open source community. And at the end, we'll go to the demo, which captures IPv6 transition scenarios as well as policy forwarding in the context of service provider. So now, this is a very quick overview of the Lisp protocol and kind of where it started. The locator ID separation protocol was designed originally to address the routing scalability in the core of the internet. And it separates the identity from location, basically splits the address space of the network into two namespaces. The identity namespace, which Lisp refers to as endpoint identity or EID space, and the routing address space, which is routing locator or RLOC space. And by splitting these two namespaces, it also, in addition to that, it creates a mapping layer, a distributed mapping database layer that captures and provides mappings of this identity space to the routing space. And with this architecture, basically, it also provides the protocol for the Lisp devices to dynamically look up this EID to locator or overlay to underlying address mapping in the mapping layer. And then the mechanism for basically doing the lookup and then encapping the packets from the identity space to inside headers of the routing space to forward the packet over the underlay network. So basically, the Lisp routers will receive packets on their LAN side within the identity space, basically, or the customer's address space. And then the routers will look up in the mapping system, in the distributed mapping system, to find out where the destination address of the packet is located within the underlay. And then they encapsulate to that address. And then they cache this mapping locally for a certain TTL. And from then on, as packets move through, there's a local cache mapping, and there's encapsulation. And on the other side, on the destination side, the routers will receive the packet, decapsulate, and forward. And then the reverse path is basically the same. With that, basically, we can go to look at the architecture overall and look at what the Lisp architecture actually provides for us. So there are three main pieces to this architecture. One, there's the data plane, which is the basic encapsulation. It provides a multi-tenant overlay, and it supports L2 and L3 overlays, and IPv4 and IPv6 encapsulation, and basically any combination. So you can do v4 and v6, v6 and v4, v6 and v6, and so on. And then there's the control plane, which includes the mapping layer and the protocol that basically the routers use to look up and retrieve mappings from the mapping layer. And the mapping layer includes basically the overlay address space mapping to the underlay address space. And this control plane and the mapping system also can include some forms of forwarding policy together with the mapping. So it's not just simple mapping, but you can have policies in the form of multi-homing, for instance, a virtual address or a overlay address space may have multiple locators, and it may have policy for reaching those. So you can say, I have priority over one routing locator to the other, or you can do load balancing between the two, so have active-active and then do load balancing between the two. And so another kind of policy is more complex path engineering policies or traffic engineering policies, in the sense that you can define not just a direct mapping, but you can give a sequence of hops or a path to go through before reaching the destination. So if you look at this architecture, basically, you can see that it's very much aligned with the core of the SDN promise, which is control plane and data plane decoupling and programmability. By modifying the policy within the mapping system, we can, the forwarding policy, and by the Lisp routers pulling that policy down, we can basically enforce various forwarding policies on the data plane and change how the packet is going to move across from the source to the destination. So now, with that, our goal of adding the Lisp service in OpenDaylight was to bring not only the Lisp protocol support to the OpenDaylight, but also the general broader Lisp architecture to ODL. And the goal was to make it such that other services, even within the ODL controller, can take advantage of this Lisp service or this architecture, or mainly the mapping layer, to be able to get overlay services from this Lisp service. And in fact, we have our integration with the first ODL service, which is the SFC service. So basically, we have a Lisp provider for SFC where we offer overlay services to the SFC project in ODL. That's the service function chaining. And I'll go into more detail of how that works later. But basically, that was the goal. So to make it to bring the architecture, the broader architecture, in a way that we offer overlay services to applications on top of ODL and also to other services within. So now, before I go to the main, yes? Question. Okay. Right. Okay. So the idea is that, right, sorry. So the question was what happens when, how does Lisp take care of changing IP addresses both on either on the routers, meaning the routing locator changes, or changes of the EIDs or the overlay space. So basically the change of the overlay space is a bit different because when you have a virtual machine, the Lisp identifies basically, if you use the IP address to identify your VM, the goal is usually to not change the IP address of the VM, but have the VM with its IP address move. So the use cases usually are have the VM with its IP address move along. So you can think of the AID to locator mapping in a way of the virtual address space to physical address space. So in the context of network virtualization, you can think my virtual machines have their IP address, and that lies in the identity space. And then the host or the switch address is basically, IP address is basically the routing address, because that's how we can get to that VM. And in that context, usually the EID is not supposed to change. If it changes, it's a new kind of node. Now, the routing locator, though, can change. So the VM can move from one host or one server to the other, or from one switch to the other, or a host can move within a Lisp site to another Lisp site, and so the routing locator would change. And all that needs to happen is updating the mapping system to account for the new mapping of this virtual address or overlay address. And that way, the Lisp routers that are pulling these mappings will be aware of the new location, and then the traffic will move. So we should have there is support for basically mobility within the overlay, and I'll go over that in more detail later. Okay, so actually that was a good segue to the next slide, which is before going into the details of the OpenDaylight service, Lisp service, I'm going to cover some of the main use cases that we're targeting with this service. So the core use case is enabling dynamic and on-demand overlay services, and that's basically the core of all the other use cases that we see here. In fact, I think Comcast recently joined the OpenDaylight community, and they announced that they were looking at, in their announcement they mentioned they're looking at using the Lisp mapping service in ODL for offering mesh VPN overlays to their customers. Within the context of overlay, then we would want to have workload mobility, meaning that we can move seamlessly across the overlay or overlay nodes across the underlying network. Think, for instance, cloud extension. So we would want to have be able to extend our overlay across to a public or private cloud seamlessly and in a secure way without any interruption. Another use case is multi-tenancy. So multi-tenancy and traffic segregation and traffic segmentation is some of the things that is all the main use cases for network virtualization. And Lisp also kind of natively supports that, be it it's VNI for VXLAN and tunnel ID, and in Lisp we have the instance ID, meaning that we can have parallel instances of the mapping system with overlapping address spaces and so on, existing concurrently together. And the traffic is marked or tagged with these instance identifiers, so we can identify and segment the traffic. The next use cases are around flexible transport. So layer 2 overlay support, layer 3 overlay support, and IPv4, IPv6 support, as well as IPv6 transition scenarios. So for IPv6 transition, we have multiple scenarios that we can look at. One would be having your IPv6 customer address space over a v4 core, or you can have a v4 site going over a v6 core. You can also have a combination where you have a v4 core over a v6 core talking to another v4 address that is only v4 core. So having disjoint address spaces and connecting through. And lastly, we talk about the policy basic use cases. So we mentioned earlier multi-homing and load balancing. Also, failover scenarios. For instance, you can have an active backup, multi-homing with active backup scenarios. If one interface or one routing locator fails, you can change the priority to the backup and still have connectivity. And lastly, traffic engineering, including service chaining that we'll talk about. In fact, HP's context stream just gave a talk yesterday, and they're using the Lisp mapping layer as a core piece of their architecture for doing advanced carrier-grade traffic engineering policies and service chaining. So with that, I'll move on to the core of the ODL service, ODL Lisp service. But these are basically just highlighting some of the use cases that we bring out in our demo. So the demo that we will show at the end of the talk will capture or bring out a subset of the use cases that we discuss here that are highlighted. Okay, so the highlighted basically components are the Lisp components within OpenDaylight. The core of it is a Lisp service, which is one of the main network services inside the OpenDaylight. And then there is the northbound APIs, which we support RESTconf and NetConf. And also, the service is completely MD-style based. So we are based on the service abstraction layer. And then there is a Lisp plugin in the southbound, which implements the control protocol for doing the lookup and retrieval of the mappings. So the Lisp service specifically mainly is focusing on that mapping database layer. So what we bring to ODL is we make ODL support that mapping of overlay to underlay address spaces, and including the policy, the forwarding policy that can be programmed there. And then we have the Lisp plugin that will enable Lisp-enabled devices to basically access that mapping layer using the Lisp protocol. We also have support in data plane support in OpenVSwitch, and so we can use OVSDB and OpenFlow to kind of emulate the Lisp control protocol and use those, but fetch the mappings basically from the Lisp service. And that's one of the things that we're working on to make it more automated later on, but even now we can have a overlay across OVS and Lisp specific devices. So that's kind of the flow of how one can use this, the ODL Lisp service. We can have, let's say, traffic engineering or load balancing applications on top, other network virtualizations or orchestrators. And through the RESTconf or basically the RPC API that we provide, we can program the mappings plus these forwarding policies into the Lisp service. And then you have the Lisp nodes or Lisp routers on the data plane that will on-demand dynamically fetch those mappings as traffic flows and enforce the policies on the forwarding path. So this captures the internals of the Lisp project in OpenDaylight. As we described, we have a northbound module. We had a northbound API basically bundle in the first release, which is now deprecated and won't be supported in future releases. And we've fully moved to RESTconf and RPC APIs, starting in Lithium. Then we have the southbound plugin, which supports the Lisp control protocol. And we have support for Neutron. So we have integration with OpenStack. We're working to improve that as well, but we have the basic initial integration right now. And what we get from there is basically whenever a VM is a new VM is created with OpenStack, a new port is created, network port is created, What we want to put into the Lisp service from that event is the mapping of the virtual machine IP address to the physical host or to the host switch that the VM is located on. And that's the kind of information that we get from Neutron. Then we have a netconf module as well, and the goal for that is to use it to automate provisioning of netconf-enabled Lisp devices. We actually show some of that, not using this module, but using the general netconf server in OpenDaylight. But we have a bundle that we try to add more automation to that process. Then there's the implementation bundle or module, basically, that has the implementation of this Lisp mapping system, which is a map server and a map resolver. These are the specific Lisp APIs to the database. And a data access layer on top that creates a separation between the backend database, and it also gives us the complex lookup mechanism that we need for doing prefix lookups and so on, which the backend database, which is now the MD style data store, is not offering yet. So we built the index, the prefix hierarchy on top of that. So going to the APIs that can be used, we have very basic RPCs. There's only two, and basically there's only one that is very important, and you can use it to do almost everything that you need, and that is mappings. So you can add mappings, remove them, update them, delete them, and that is mapping of an EID as an input, and then or a virtual address as an input, and a mapping it into the underlying address. Then there is the key resource, which we can, again, add, update, get, and so on. And that's basically a password or a key between the Lisp devices and the mapping database that is used for security. If you want to accept write operations from the Lisp data plane devices. Then there's, of course, RESTconf that gives you access to the database directly. The RPCs should mainly be used as when using the service, because they, using the RPC, we build the processes of longest prefix matching and so on. The RPC goes directly to the database. It's kind of like the admin going to the database and deleting something or changing something directly. Then, in terms of what kinds of mappings we support, basically, we have, as I said, v4, v6, and MAC or Ethernet mappings, and also some more complicated ones, like we have two-tuple mappings for source dest, where you can, it's not just the destination that you map to a location, but you define policy between a combination of source and destination, or a two-tuple. Then traffic engineering and service chaining that we discussed, so defining a sequence of hops instead of just a destination. Then we have distinguished names and AS numbers and segment ID, which is that segmentation of the traffic that we talked about. This is an example of the API. I won't go into the details, but the high-level items that we want to kind of bring out here is that we use the RESTconf API, and there is, at the end, when you add a mapping, the main components that you're doing is adding the EID as an input and saying that the mapping for that is the address in the bottom. So, and then there are parameters like priority and weight and so on that are all embedded within Lisp, which is what is used for multi-homing and load balancing policies. But at the end, what you're saying is that that's my virtual address, and it's mapped to this physical address. And then the routers will look up the virtual address, and they will get the physical address to encapsulate to. So back to the architecture, and we talked about SFC. So we have already in Lithium integration with the service function chaining. You can actually go to the Deluxe GUI of SFC, and if you have Lisp elements already connected, you can define a chain in SFC, and that will, if all of your chain nodes actually support Lisp, then we put this chain, define it in the Lisp mapping layer, and you can actually execute the chain using the Lisp nodes. So that integration is already there. You can go play with it and use the GUI to create a Lisp chain and see how that works. The other thing is the neutron support, which I kind of covered. And in terms of where we want to go for the next releases, one of the main things that we want to do, as I said, is offer the Lisp overlay services to other OpenDaylight services. And we started with SFC, and we're looking at improving that by supporting NSH as well, because this is just a Lisp overlay chain, not the Lithium release doesn't have NSH support for SFC, but we are adding that in Beryllium. And also, maybe we're looking at integration with group-based policy, so we can use GBP to program policies in our mapping database and then enforce that in the forwarding plane. As I said, we're also looking at a better and automated integration with OpenFlow and OBSDB, so we can actually kind of translate and look up mappings and translate that into an OpenFlow rule. So we can have a dynamic overlay across OBS switches as well as Lisp devices. We're also looking at better, adding GUI integration, not just through SFC and group-based policy, but also to the Lisp service directly. So you can kind of look at, using the GUI, you can look at what is in the mapping system and how does the overlay look like, and so on. Yes? Question?
My understanding is that you don't really have HA available yet in OpenDaylight. I could be wrong with that. But if you looked into, I mean, since the mapping agent is so critical in the Lisp environment, do you have any work planned for HA and nonstop forwarding sort of function?
Right, absolutely. So that's a very good point. We are using in the backend the MD-SAL data store, which supports clustering and persistence. So we are based on that. We take advantage of the persistence of the MD-SAL service. And in terms of clustering, that's and scalability, horizontal scalability, that's one of our targets for Beryllium to focus on that more. I think that achieving just in terms of high availability, so active or active backup scenarios, is fine with our current architecture, just using the clustering from MD-SAL, although we still have to kind of play with that and test it, but overall the architecture is aligned and we can just take advantage of that. But regarding sharding, basically, or segmenting the database across, then that will need a little bit more work that we hope to do in Beryllium. But yeah, high availability, I think, is very aligned, and we can take advantage of the MD-SAL to give us that. Another thing that we're looking at is storing, transport capabilities as well in the mapping system. So if you have, as you noticed, we don't talk about the encapsulation and what that is, because that really can be anything. It can be GRE, it can be VXLAN, VXLAN GP, and so on. Oops. So one thing that we're looking at is to store the NCAP capability or the transport capabilities of nodes as well. So when you map the virtual address to an underlay address, you also say that underlay address, what kinds of transport does it support? And so that way we can provide that information, and if there is multiple transport forms support, then we can do a selection of those. Okay. So that was the quick overview of what we have in our Lithium release. Now, Lisp in open source. So we have a lot of availability there. The main place to refer to is the lispmob.org. That is open source implementation of the Lisp tunnel routers. And also it's available on Android and OpenDaylight. So in fact, some of our members have been running Lisp on their Android phones for a couple of years now. And that's the phone that they use. So we eat our food. Yeah, so the other places in OpenVSwitch, as I said, we have Lisp data plane support in OVS. And also we have mapping database support in ODL, as we just saw, and also the Lisp control protocol support as a plugin. And then there's also Wireshark support for the Lisp encapsulation and the control protocol. So you can run Wireshark and see Lisp control protocol control messages, and it dissects the header, and you can see everything there, which is very helpful for development and debugging. And now LispMob has netconf support, which is one of the parts that we're going to show in the demo now. So we can actually provision LispMob, which is the open source Lisp implementation on Linux, with netconf and dynamically modify that. Okay, so with that, I think we can go over to the demo scenario. Any questions so far? Or we can start with the demo. And that kind of captures actually some of the more detailed use case scenarios. Okay. So the demo scenario is showcasing a service provider using the OpenDaylight controller to offer connectivity and overlay services to its customers. So here we have a blue customer, which has a data center and a couple of branches connected over a v4 core. We also have a red customer with a data center connected to v4 core and a couple of branches connected also over the v4 core. So eventually we have, we'll see more and more use cases where such customers may have remote branches that have to connect over a v6 only core. And that's the kind of IPv6 transition use case that we're showing. So first of all, we can have a v4 customer site that is connecting over a v6 core to the service provider network, and also connecting to, let's say, its data center or main campus that is only v4 connectivity. So we enable that by one of the Lisp elements that is called the re-encapsulating tunnel router, which is a typical Lisp router that gets encapsulated packets, it decapsulates them, and does another lookup to see now where it has to send it. And then encapsulates again and sends and moves it forward. So that's basically a Lisp element that we can add in between, and together with the multi-homing of these RTRs, we can have an RTR that has connectivity both to the v6 core and to the v4 core, and have our red client branch that is v6 only go over this RTR, and that way provide connectivity to the v4 only data center for it. So we'll focus on these four kind of slides for now. And in the demo, the first phase is to do the provisioning of the routers. So we have, in terms of deployment, we have 4 sites, and we have 4 Lisp routers, and these are all LispMob, so Lisp implementation on Linux. And we use netconf server in ODL to connect to these Lisp routers and configure them, provision them for use with this network. After that, we go to the northbound REST API or RESTconf API of OpenDaylight, and we introduced the mappings of these sites to actually enable the overlay to offer connectivity. So as you can see, we have basically the blue customer. They has two sites or two prefixes. The client sites or the branches are is 1.1.1/24, and the server is 10.10.10/24. And so we have the mappings for those. They're both IPv4. They're mapped to a single IPv4 connection. Then we have the red customer, which has, again, two sites, the data center, and then the branch that is over v6. And as you can see, in order to enable connectivity over v6, what the service provider can do is offer these RTRs as a service to the customer. So the customer can go and say, I have this v6 only branch or v4 branch that is connected to a v6 core, and I need to provide connectivity to it to the v4 address. So it kind of uses or requests an RTR service. And the RTR has a v6 interface or a v6 locator and a v4 locator. So on the first row for basically here on the first row for the server 2 or the red customer site basically, you can see that we have the IPv4 address for that, which is the IPv4 address of the Lisp router. And then we have the second locator, which is a traffic engineering policy in a sense that it has two hops. There is the first hop, which is an IPv6 hop, which is the routing locator of the RTR here, and then the IPv4 address of the site itself. So this says that you can reach this, the server 2 or the data center of the customer 2, any address within that space, by over a v4 going to this address, or over v6 going to this address first, and then finally you will reach there. The same goes for the client, so it's the reverse path. The client is v6 only, and then it also has a v4 to v6 path for the reverse path. So with that, we have traffic flowing, so we can show that the client 2 can go over this RTR service and reach its server in the v4 only core. And we have the typical v4 to v4 between customer blue. Now let's say that the blue customer is also adding branches over the v6 core. And so we have this additional client that we want to provide connectivity to. Again, the blue customer can go to the service provider and through ODL ask for another RTR service and add its client 3 or the second branch, blue branch. We would define the mappings by, again, introducing the v6 mapping, which is its direct mapping, and also a v4 mapping through the RTR address. And then we will see that traffic connectivity between the branch to the server 1 is also enabled. And here we show, so we're showing, in the demo we show pings between the client 1, the first branch, and the data center branches. And then for this third branch, we're showing a video download. And the reason for that is that we want to show how you can insert additional policy by the service provider, for instance, to balance the load across, let's say, the RTR services that it's offering. So basically, the service provider can go and say, I have maybe too much load now on this RTR, and I want to move my traffic from this to another RTR service. So you can update the mappings. The service provider can go to the ODL and update the mappings for those and introduce the new RTR for connectivity between server 1 and client 3. And that way, the traffic will flow from this client through the second RTR and reaching the destination. And so in the demo, we show a video with VLC server, no caching or buffering, basically. And still, we see no changes and only, we have a couple of packet losses if the previous mapping, if the state on the RTR is, on the new RTR service is null, meaning we don't have anything cached yet, and it's the first time it's offering the service, then there will be a couple of packet losses until the RTR will fetch the new mapping, and from then on, then the traffic will flow smoothly. So now we're going to use in the demo the direct REST-conf API to the Lisp service, but you could also technically use SFC GUI to, for instance, add these RTRs as a service in the middle of the path, and that would work fine as well. Okay, so with that, I think we can go to the actual demo. And I'll give this to Alberto.
Yeah. Thank you, Vina, for the nice talk.
Mm-hmm.
Okay, so let's move on to the demo. Hopefully it will work fine. Okay, so what I'm going to do first is we have all these Lisp devices on the data plane, and I'm going to first establish connections from ODL via netconf, and then I will push the configuration so they will be Lisp ready. Okay, so we are using, I'm going to show you the RESTconf calls and so on Postman, but then later I will send them all at once through CLI. So for instance, if we want to establish a connection to the client one device, so we have here the name of the connection that we want to establish, and we need to provide the IP and the IP and the port for the SSH that we use to connect through netconf, and we need to provide the user and password. So basically, all of these are just establishing connections to all the devices. So now, if we come here and we send this one, this will send all at once all these that you see here that basically are establishing connections, netconf connections to all the devices. So, okay, there you go. No, sorry, not this one, but this one, okay. So we wait a bit because it takes a while. So you see that it's a bit by bit establishing connection with all of them. Okay, we are good to go. So now there's a connection with all of them, and what we are going to do is to configure the devices, the Lisp devices. Basically, what we are going to configure them with is with the IP of the mapping system. So we are telling them, okay, if you want to use the Lisp setup, you can reach this guy which knows the mappings that you need. So
that's the OpenDaylight server.
Basically, it's the OpenDaylight service. Okay, so we send this configuration to all of them. Here. Okay, we got all the configuration. Okay, now we will insert the Lisp configuration for the mapping. So, for instance, I don't know, for client one, we will say, okay, you can reach this Lisp site in this IP, which are the IPs that are shown in the slides as well, right? So we send the mappings with this, and now let's go and see one of them to see that everything is all right. So, for instance, let's check. First one. So now we are sending another request like, okay, I want to get the mapping for this guy. So we send the thing and we get, okay, the guy is here. So with that, we have all that we need. So we have all the Lisp devices up and running, configured, and we have all the mapping information on ODL. So we are good to start doing tests. So what I'm going to do first, I'm going to ping from client 1 to server 1 through just IPv4. I'm going to ping from client 2 to server 1 using the RTR.
To server 2, right?
The server 2, sorry, yeah. So let's ping server 1 from client 1, which is going through IPv4 only. It's going to take a bit because it needs to populate like the map cache. You see, we have a bit of loss, but once it's running, it keeps running. I'm going to do the same thing from client 2 to server 2. We are going to have a bit more of losses because we have to go through the RTR as well, but it's going to be quite okay. So you see, now we also have connectivity. And now, in the mappings that we have, if we check the mapping, for instance, for the server 1, we'll see that it's only reachable. You see, this is server 1, so it's only reachable through this IP in the physical network. So there is no way at this point for client 3 to reach server 1. So let's do a ping to check that it's not working. Let's wait a bit, okay? No, it's not working. So what we are going to do now is we are going to update the mapping for server 1, so client 3 will be able to reach it. What we are going to do basically is going to say, okay, server 1, you can reach it, even if you're in IPv6, you can reach it using RTR1. For that, we use this thing. So we say, okay, this mapping, which is server 1, can be reached either by directly connecting over IPv4, and if you are not lucky and you don't have any IPv4 connectivity, then you can also use this detour over this is the IP of the RTR. So you can go through a set of hops. First, go to the RTR on IPv6. Then from there, you can go to the address in IPv4. You can follow this path over here. So we send the mapping. And hopefully, all the data plane devices will get updated. And yeah, we have connectivity now. Cool. So now to the best part, the video.
So just add one thing. As you see, the connectivity is kind of instantaneous. So what we did in the ODL mapping service is to enable a kind of a publish-subscribe mechanism where we kind of carry we cache a set of subscribers for a specific address. So let's say your Lisp router queried or looked up an address not long ago, and now that address has changed. So once we store this a set of subscribers basically to every address or every address in the overlay, and if there's changes to that overlay address, we push a notification to all of the cached subscribers for that address to say that there's new mapping there and you should use the new addresses for that. So that's why instantaneously when you have a new node, a new mapping, or adding a new mapping or changing the load, as Alberto will show, we will quickly see the result in the network.
Yeah, exactly. That's it. So, okay, I'm going to check that the video is doing well. So we have here a VLC server waiting for connections to stream the video. So now I'm going to put the load of the RTR. So we are showing here the network network load that we have in both RTRs. So the window in the top is RTR1, and the window in the bottom is RTR2. So you can see them. We have RTR1 and RTR2. And we have also the graphical interface for client 3. I don't know if you can see it, but we are disabled caching here. So you see that we are using network caching equals 0. So okay, there you go. Have this nice all movie for you today. Okay, so with this up and running, you see that the load here increased because we have established the video streaming through RTR1. So RTR1 is receiving all the video. So now let's switch this to the RTR2. So we will basically move the load that is going from server 1 to client 3 towards the RTR2. In order to do so, we modify the mappings and we tell them, okay, use RTR2 instead of RTR1. Send this thing in. Okay. Now, if we are lucky, yeah. Okay.
So again, with that subscription list, we kind of, because this the client 3 is already downloading from that server, we have it as a cache subscriber, and we notify it right away. So.
Okay, let me restart this thing just for a second. Okay. Okay. So we have restarted RTRs just to check the configuration is okay. We'll make sure that everything is all right. Okay. Stuff, of course. Okay. Yeah, basically put it all clean state, I hope. So we won't have problems this time. And then we start streaming the thing. Okay. And at some point it got lost, whatever. Okay, so maybe you are not seeing the video today.
What happened? Oh.
Interesting.
Do you want to restart your turn?
Everything?
Okay.
Okay.
This stuff thing.
Okay, let's start.
Okay.
Let's start even ODL.
For ODL is not even.
No, but just in case we can.
Okay. So we're getting some minor difficulties, but.
You know how live demos are, so. Okay. And the RTS as well. We have time since ODL is restarting. It takes a bit, so. Okay. We're almost done here. This is the last one. Don't hate me that much, guys. Okay, you go. We connect to all. Oh, ODL is not up and running yet. Oh, damn it, I didn't start it.
You didn't want to unzip it?
Hmm?
You didn't want to unzip the original?
No, you're right, yeah.
Control D.
Yeah. Okay. Okay.
Okay. 2 more minutes. So while Alberto is running, if there are any questions, we can go over them because I think after we have to kind of wrap up. Laurie, did you want to add anything? No?
Okay. How are you doing, ODL?
Did you add? Oh, it's not loading yet.
No, it's still loading.
Sure. Can you repeat that? Right. So we can. So what I was just describing is that in terms of the high availability case as well. So we can run multiple OpenDaylights per site in terms of high availability. If you want to have synchrony between them, we can also use the MD-style clustering to cluster the ODL instances. But we don't do sharding right now. So we can't separate the spaces across them. Every mapping system will have the entire state. So doing the sharding is something we're working on for Beryllium.
Okay, let's try this time. Okay, now we are reaching ODL. The configuration.
All right, okay. Do you want to run it, or how long?
It's gonna be like, you wanna stop now?
No, we can go ahead.
Okay.
Yeah, I think we have to stop because we're already a few minutes over.